Good morning, everyone, and welcome to today's presentation. I'm Dr. S.K. Singh, and I hold a PhD in this field. Today, we will be exploring the fascinating world of HPLC columns. The topic is types of HPLC columns and their applications. Over the course of this session, we'll look at different types of columns used in HPLC and discuss how each one is applied in various analytical scenarios. I'm excited to share this knowledge with you, so let's get started. Welcome to our discussion on HPLC, or high-performance liquid chromatography. This is a powerful analytical technique that we use to separate, identify, and quantify different components within a mixture. Essentially, it helps us analyze complex samples with great precision. The core of HPLC relies on the interaction between two phases: the stationary phase, which is contained within the column, and the mobile phase, which is the solvent that flows through the system. Think of it as a dance between these two phases, where different components in your sample will interact differently, allowing us to separate them effectively. The column itself is the heart of the HPLC system. It's where the actual separation occurs. Everything hinges on how well this column performs, making its quality and design crucial for accurate results. As we move through this presentation, keep in mind that understanding these interactions and the role of the column will help us grasp how HPLC achieves such precise separation and analysis. Let's talk about the importance of HPLC columns. These columns are really central to the whole process because they determine several key aspects of our analysis. First, they influence separation efficiency, meaning how well we can separate different compounds in a mixture. Better efficiency leads to clearer, more distinct results. Next is resolution, which is about how well we can distinguish between closely related compounds. And then there's selectivity, or the ability of the column to target specific compounds based on their unique properties. Because different compounds have different chemical characteristics, we use various types of columns tailored for each one. For example, there are columns designed specifically for polar compounds, and others optimized for nonpolar substances. We also have columns suited for ionic compounds, which are charged, and for biomolecules like proteins and nucleic acids. Choosing the right column is crucial because it directly impacts the effectiveness of our separation and, ultimately, the accuracy of our results. So, understanding these differences helps us select the best column for each specific analysis, connecting directly to our overall goal of achieving precise and reliable separations. Now, let's take a closer look at the classification of HPLC columns. HPLC columns are mainly categorized into several types, each with its unique characteristics and applications. First, we have the normal phase columns, which are typically used when we want to separate compounds based on polarity differences, with the stationary phase being more polar than the mobile phase. Next, there are the reverse phase columns, which are the most commonly used in analytical chemistry today. These have a nonpolar stationary phase and a polar mobile phase, making them ideal for a wide range of compounds. Then, we have ion exchange columns, which are specialized for separating ions and polar molecules based on their charge interactions. Moving on, size exclusion columns work by separating molecules based on their size, allowing us to analyze complex mixtures like proteins or polymers. There's also affinity columns, which rely on specific biological interactions, such as antigen-antibody or enzyme-substrate bindings, to achieve highly selective separations. Lastly, we have specialty columns, including chiral columns, which are designed to differentiate enantiomers, mirror image molecules that are otherwise very similar. Understanding these classifications helps us choose the right column for the specific separation task at hand, ensuring accuracy and efficiency in our analyses. Let's take a closer look at the uses of normal phase columns. These are particularly useful for analyzing fat-soluble vitamins like D, E, and K, as well as steroids. You'll notice that they find applications in both the pharmaceutical industries and food chemistry, which highlights their versatility. In terms of how they work, the stationary phase in normal phase chromatography is polar, such as silica, while the mobile phase is nonpolar, like hexane. This setup allows separation based primarily on polarity differences. For example, it's especially effective in separating lipids and isomers. Common materials used for the stationary phase include silica, which is quite standard, and amino columns, which can offer some specific selectivity. Overall, normal phase chromatography is a powerful tool when you need to separate compounds based on polarity, especially in complex mixtures like lipids and vitamins. Now let's take a closer look at reverse phase columns. In this setup, the stationary phase is nonpolar, typically made of materials like C18 or C8. The mobile phase, on the other hand, is polar, usually a mixture of water with methanol or acetonitrile. The separation process relies on hydrophobic interactions, so compounds that are more hydrophobic tend to stick to the stationary phase longer, while more polar compounds elute faster. For example, this method is commonly used for analyzing drug compounds and peptides. When it comes to the different types of reverse phase columns, C18, also known as ODS, is by far the most widely used because of its strong hydrophobicity. Then there's C8, which is less hydrophobic, making it suitable for certain applications. And for proteins, we often use C4 columns. They're less hydrophobic still, which helps in separating larger molecules like proteins without causing them to stick too tightly. For instance, C18 columns are excellent for antibiotics analysis, while C4 columns are better suited for protein separation. Recognizing these differences helps us choose the right column to optimize our separation process based on what we're analyzing. Now, let's take a look at some of the key uses of ion exchange columns. These columns are incredibly versatile and are used in a variety of fields. For example, they play a crucial role in water purification analysis, helping us remove unwanted ions to produce clean drinking water. They're also essential in protein purification, where we separate specific proteins from complex mixtures. In pharmaceutical quality control, ion exchange columns help ensure the products meet strict standards by isolating or removing certain ions or molecules. To illustrate this further, consider the separation of sodium, potassium, and calcium ions. These are common examples of ions that can be separated using ion exchange techniques. The core principle behind their function is separation based on charge. The columns come in two main types: cation exchange, which targets positive ions, and anion exchange, which is for negative ions. For instance, in protein and amino acid separation, these techniques are invaluable because they allow us to selectively isolate molecules based on their charge properties. Similarly, inorganic ions like those in water samples can be separated efficiently. So overall, ion exchange columns are a powerful tool in analytical chemistry, biochemistry, and environmental science, enabling us to purify, analyze, and control the composition of complex mixtures with precision. Now, let's look at some common uses of size exclusion columns, or SEC, also known as gel filtration. One key application is in determining the molecular weight of proteins. This technique allows us to estimate the size of a protein based on how it moves through the column. It's also widely used in polymer analysis, helping us understand the size distribution of polymer chains. In biopharmaceutical research, SEC plays a crucial role, especially when analyzing complex biological samples. For example, it can be used to separate insulin from its aggregates, ensuring purity and stability. The core principle behind SEC is simple but powerful. Separation is based purely on molecular size. Unlike other chromatography methods, there's no chemical interaction involved. Instead, larger molecules, like proteins or polymers, are excluded from the pores within the beads and thus elute first. Smaller molecules, on the other hand, enter the pores and take longer to pass through the column, so they elute later. To sum up, SEC is an elegant way to separate molecules based on size, making it invaluable in many research and pharmaceutical applications. Let's take a closer look at affinity columns. These columns are based on specific binding interactions, which means they rely on highly selective processes. The key idea here is that the interactions are very specific, allowing us to target particular molecules with precision. For example, one common interaction is between an antigen and an antibody. This binding is highly selective, making it perfect for isolating or detecting specific proteins. Another example is enzyme-substrate interactions, where enzymes recognize and bind to their specific substrates to catalyze reactions. These highly selective interactions are fundamental to many biochemical techniques, especially in purification and analysis, because they ensure that only the molecules of interest are captured or separated. This specificity is what makes affinity columns so powerful in research and diagnostics, as they allow us to target and isolate specific biomolecules with great accuracy. Now, let's take a look at some specialized columns used in chromatography. First up are chiral columns. These are really important because they allow us to separate enantiomers, which are mirror image molecules. This is especially crucial in drug development, where the different enantiomers can have very different biological effects. Being able to distinguish and isolate these enantiomers can make a huge difference in creating safe and effective medications. Next, we have HPLC columns, which are designed for highly polar compounds. These columns are particularly useful when dealing with substances that are very water-soluble. For example, an interesting application is the separation of enantiomers of ibuprofen, which demonstrates how HPLC can be used to analyze and separate chiral drugs effectively. Overall, these specialty columns expand our capabilities in chromatography, allowing us to handle complex molecules with precision. Whether it's separating enantiomers for pharmaceutical purposes or working with highly polar compounds in various analytical contexts. Let's take a closer look at the comparison of HPLC columns. As you can see, different columns are designed for specific applications, and choosing the right one is crucial for effective separation. Factors like column material, dimensions, and particle size all influence the quality of your results. For example, smaller particle sizes generally offer better resolution and faster analysis times, but they also come with increased back pressure. Conversely, longer columns can improve separation, but might take more time. It's important to consider the nature of your sample and your analytical goals when selecting a column. This comparison helps us understand how to optimize our chromatography setup, ensuring we get accurate, reliable data tailored to our specific needs. Let's wrap up with some key takeaways. Choosing the right HPLC column is absolutely crucial because it directly impacts the accuracy of your results, the efficiency of your analysis, and the resolution you can achieve between different compounds. Remember, not all columns are created equal. Different types are tailored for specific applications, so selecting the appropriate one makes a big difference. The most commonly used columns are reverse phase columns, and for good reason. They offer versatility and broad applicability across many samples. But as technology advances, we now have access to specialized columns that enable us to analyze complex biomolecules more effectively. Overall, understanding these differences helps us optimize our chromatography methods and ensures we get reliable, precise data every time. For further support, please feel free to contact us. We're here to help with any questions or additional information you might need. And with that, I want to sincerely thank you for your time and attention today. Your engagement is what makes these discussions meaningful, and I hope you found the presentation valuable. Remember, we're always available to assist you as you apply these concepts. Thank you again, and have a great day.